Thanks, Chris, for the nice introduction. I would like to start with acknowledgements. This project is a heavily collaborative work with Caltrans engineers, which we call them the team. I have put their names up there: Sharon, Mark, Tony, different folks who are in our meetings talking about how we can make this work implementable and applied for the engineers. And the work, as I'll be showing you later, it is basically taking performance-based design in a direct way and implement it in SDC. We also have a project advisory board. Said Saidi and Norm Abramson are there, making sure that our work is rigorous enough and it passes the test in the academic side. On the bottom row, I have three other mentions. Peer, during my career and for this project, has been super helpful and resourceful in making sure that whatever we need is available for us to push the research envelope forward. Saurabh Singhal, who's the graduate student who's working day and night to make everything happen. As I will show you, we have quite a lot of work done. And Chris Traina, who is the coach and the champion for making sure that the work that we do passes through the labyrinths of decision making and making sure that the next version of SDC has some of the work that we do here implemented. So with that, also I'd like to acknowledge Caltrans because we are all working under that envelope. So as I mentioned earlier, and I didn't see anyone putting in their presentation, I want to mention about our 4 random variables in peer, the seismic hazard, the intensity measure, the engineering demand parameter, the damage measure, and the decision variable. What we're trying to do in this project is to take SDC to the next level. Right now, the seismic design criteria, known as SDC, designs bridge columns using a ductility factor, or ductility demand, ductility capacity. Ductility is being used as a surrogate for damage. We're trying to bring in damage directly into the decision-making process. And I have put here some of the familiar, let's say, graphics. We want to make sure that the work that we do doesn't change the life of a design engineer by much. Eventually, they need to change the parameter that they're going to use for design from ductility to something else. But we're trying to make sure that as much possible we're using the old terminologies, the old tools that they have that makes this transition less painful. Now, the process, as was documented by Yoon and co-workers in several publications and ASC structures, the process follows the flowchart that you see here. Our work in this project tries to ease development of information here. But before I get there, let me show you how this works. The engineer comes up with a column geometry and proportions the column according to their experience. From there, they do a pushover analysis, which basically means doing a moment curvature analysis and coming up with a basic estimate of demand. Now, demand in this case is no longer ductility. It's a new character called damage index, which I have put the equation for calculating damage index down here. It basically means how much the column passed into the plastic region and how far is it from yield and how close is it to ultimate capacity. The numerator is demand minus yield point in displacement, and the denominator is the ultimate capacity minus the yield. So let's say if this character becomes 1, that means you are at the ultimate state, and that column can be considered to be quote-unquote collapsed. So we like the designer to gauge this parameter at 0.35, but we are trying to figure out what should be that parameter for a target design. More for you to see later. And if there is a need for adjustment, this part is being redone. The main part for assessment happens down here, which is following the peer integral, but I'm going to show you how it works. So for the assessment part, we do a regular, nice IM-EDP analysis. Modeling the column in open seas is what we do, but the engineers have a different way of doing things. They're using X-section. We have validated our models to ensure that the outcome of our models in open seas follows the X-section process, and we have also validated our analytical model with test results. I'm going to show all of that later. And a cool IM-EDP curve is generated. This information is being used in conjunction with the capacity side, which is from the test results at UNR. The fragility curves were generated by Said Saidi and co-workers, and we're just utilizing that. And then all of this is put into a convolution integral, which collapses out the EDP. In order to implement this integral, which I'm just showing it in a graphical form, we are using the reliability beta factor, which happens to be this nice looking equation, assuming that DI, which is the damage index, which is our EDP, is log-normally distributed both on the demand side and the capacity side. The equation of this form comes up, betas are calculated, and for the work that we are doing, this beta is calculated for 3 different hazard levels of 225, 975, and 2475. And from there we fit a distribution there, which is our quote-unquote fragility curve. Relationship between intensity measure and damage index. And damage state, damage state. We integrate this fragility curve over the hazard curve, which a mean annual frequency of exceeding a damage state emerges, and from there we put it in a Poisson process, and from there risk is calculated. So all of that is what we have done. What we're trying to do is to give engineers the tools that they can calculate that mu and sigma showed in the equation with delta, which is the coefficient of variation. This project is trying to make this part easy for the engineers, that the rest of the flowchart is easily implementable. This is the most expensive part of that flowchart. And for doing this, we have I jumped to the next slide in my mind. We have developed the maps. I have blurred them out. I want you to know that we have maps for this delta L, and we do have maps for that adjustment factor, which shows how much should be the adjustment to the estimate of demand using the simplified approach to get to the median from the nonlinear time history approach. But I blurred them out because we're still going for publication. This is not ready for showing to the public. This was under the advice of counsel, so take it from there. Now, how did we come up with this? We divided California into the grids of 25 by 25 miles. For some interesting regions like the Bay Area, Los Angeles, Northern and Southern California, San Diego, and Eureka, we have more finer grids, like 5 mile by 5 mile. And we have a slew of columns from column heights of 20 to 50 feet, axial force ratio 5% to 15%, longitudinal reinforcement ratio 1% to 2.5%, diameters from 5 to 8, and rebar sizes and rebar spacing. So this creates a lot of columns. For each one of these points that you see on the California map, we have identified what are the columns that will give you a damage index between 0.3 and 0.4. These are acceptable designs according to a Caltrans engineer. So from there, we are simulating and scaling ground motions to match the hazard of that location. We're running that into the models and assess displacement, and from there the damage index, which from the damage index output of the simulations, we are generating the maps. For each one of the hazard levels of 225, 975, and 2475, we're simulating and scaling 51 ground motions. This is deemed necessary because we not only want to estimate what is the mean or median, but we also want to estimate COV, which is variation, and for variation we need a lot of simulations. 51 is a number that we think it is enough to capture the variation. Now, we have done some validation. I mentioned about the validation that our model has with X section. In other words, the moment curvature that our OpenSeas model generates is similar, almost identical to the moment curvature that X section generates. We have taken the work by Lehman and Milley, which they looked into well-confined columns, Caltrans columns in early 2000 with different aspect ratios, different reinforcement ratio. We didn't look at this 0.75 because it's outside the scope of our work. And here you see the force deformation that we get from our modeling approach We didn't tweak our models at all. We just put the amount of reinforcement, the information that was shared in the report, we put in our model, and this is the force deformation that you get. So in the red color is our models, the blue color is from the experimental, and more or less looks good based on my limited knowledge of how validations are done. We have also validated our ground motion representation. We are simulating our ground motion using Armin der-Kurion's approach, which was the work by Zareian and der-Kurion and Dabori and der-Kurion. We are validating that simulation and scaling by making sure that not only we match the main intensity measure, which is the spectral acceleration, but also the simulations match a secondary ion. There is a good amount of work by Norm Abramson, who has generated these conditional ground motion models. A ground motion model tells you what is the intensity measure given the event parameter. The conditional models do the same, but it has an extra conditioning, and that conditioning is on another ion. We call it the conditioning ion. So we have done some validation for 4 different locations with 3 different hazard levels. So we have done our work, and eventually we have identified that the parameter that is important to ensure it is well represented is PGV. We are making sure that the PGV of each one of those sets, the 51 ground motions for each one of the hazard levels, falls within the 20, for each one of the events in the return periods that I just mentioned, not only match in median between 25% and 75%, but also covers the range between 5% and 95% of possibility. So with that, this was supposedly the map that I show you. This is the COV for 225, 975, and 2475. The maps, as you can see, there is a control map. This is not like something that is constant everywhere and for different locations, but this is for LA, this is for Bay Area, and this is for the LA area. The maps are kind of have a better contouring. Now, I didn't know that PowerPoint can do such a great job in blurring the information, but this is well blurred out. Anyway, and this is the adjustment factor. I can use the time to tell you what is the adjustment factor. Usually, Caltrans engineers use a moment curvature approach to come up with an estimate of the displacement. This is called the ESA displacement, let's say. That displacement needs to be magnified to incorporate the nonlinear action and what you will get once you input a ground motion, rather than using spectral analysis. This factor, what we call it the phi factor, basically is adjustment to that estimate. And we have also developed an app which we have shared with Caltrans. The engineer puts the latitude and longitude and the site class. It connects to the USGS, collects information. It can also use the maps, and it will blur out what would be the these factors. So the engineer doesn't need to go and use the magnifying glass to use the contour maps. Now, given that I have a few minutes, I will take my time to present to you how all of this can be utilized. Let's say that we have a bridge, 30 feet column height, geometry of the deck is given. We, as a part of this project, try to put in contrast what would happen if we embraced a risk-targeted ground motion approach. From the building industry, ASC 710, I think, since ASC 710, we are using MCER, which was calibrated to have a 1% probability of incipient collapse in 50 years for any new design. A fragility curve for collapse is assumed. The dispersion is assumed, and the median is varied in order to arrive at that collapse probability in 50 years of that risk. From that calibration, maps are generated, which we have, there is a similar effort happening from the AASHTO side to do risk-targeted ground motions for the bridge work. We have taken that work and we have plotted that spectrum on this plot for you in conjunction with the UHS for 225, 975, and 2475. An RTGM spectrum does not lend itself to a target return period because the methodology that is being developed, each point on the spectrum has a different return period. But it happens to be that it's close to our 970, right? So we would like to see what would be the design. This bridge is already designed, and let's see what would be the estimate for the risks if we follow our approach for assessing the risk. So risk targeted ground motion, fragility curve, there's no assessment of that. This is the assumed fragility curve for developing the UHS. And 1.5% risk is what is being promised by a risk targeted ground motion development method. Doing the assessment realizes that the true fragility curve is this one. It's a little bit different from what is being assumed, which is not too bad. It's still in the ballpark. And the assessed risk is 2.5%. So again, it's not 1.5%, but it's, again, 2.5% close enough. But if we use the work that we have done, you can change hoop size and hoop spacing, do direct assessment again, and now design for the target risk. So in other words, if you are truly targeting a 1.5% in 75 years, you want to use a hoop spacing of size 8 with 7H. That's the quality of the work that we are providing with the research center. Now, we're taking this step forward. We are doing two things. One is we're generating archetype bridges. We're generating archetype bridges using this approach. For each column, we are coming up with a deck width, thickness, length that can give you the correct axial loading on that column. And from this side, we are also assuming the reinforcement. If we get to a target geometry, if things converge, we take that geometry and put it into our automated OpenSeas models, which basically is an input for all of this crazy model that you see here. And it runs the ground motions into it. And from here, we want to see how good, bad, or ugly our estimates of damage index as being if we use a single column model versus a full bridge model. We are also doing 100 bridges, as-built bridges that are out there that are being used, and see what is the risk of our current practice. And with these, we would like to calibrate what should be the damage index that the design engineer will use to calibrate their future model. I hope that this was not 100 miles per hour, but that's all I had for you. Summary of the work. We have a method that can give you a good design. It's easily be tailored. We have put our work in contracts with the RTGM approach, and I just explained what is our future state. I'll make myself available during lunch that I can answer your questions. Thank you very much.